welcome back to lectures on advanced calculus for engineers, and this is the last lecture of this module, and here we are on lecture number 20 on maxima and minima, and this is the last part on this maxima and minima. So in this lecture we will discuss the method of Lagrange multiplier, and there will be many worked problems based on the Lagrange approach. So what is the method of Lagrange multiplier? Let's go into the details. So now the question is, find the maxima minima of the function u is equal to fxy, and there are some constraints. So with the constraint, suppose phi xy is equal to 0. So we want to maximize or minimize this function fxy, but under certain restrictions on x and y. So now if we want to derive that how to find the maxima minima of this problem, using the chain rule, what we know, because here u is a function of x and y, and then x and y are related by this relation. So we can use that chain rule which we have studied in the calculus functions of two variables. So here del du over dx, we can talk about du over dx, because here the function is given as a function of x and y, and then here y and x are related. So y is a function of x again by this relation. So with this we can have here du over dx, because u is a function of one variable. It is a function of two variables given here, but then y is again a function of x. So at the end u is a function of x, and we can directly, using this chain rule, we can find out du over dx. So this du over dx is del f over del x and dx over dx, that is 1, and del f over del y, and then we have here dy over dx. So with this chain rule, and at the point of extrema, because if we look at the problem, it is a problem of functions of one variable. Here we have two variables, but one we can substitute from this relation. So at the end u is a function of one variable, and therefore we have here du over dx. So we are back to the problem of functions of one variable. Now we know that at the point of extrema, what should happen, that du over dx must be 0. So this du over dx must be 0 at the point of extrema. Now with this du over dx, we got a relation that del f over del x plus del f over del y and dy over dx must be 0. So that is the one relation we have at the point of extrema. Well, now having this relation, we will look for some more. The equation phi xy is equal to 0 is also satisfied at any point, and therefore at the point of extrema also we will have phi xy is equal to 0, because that is the restriction along with that function u we have. So whatever point we are talking about, the phi xy must be 0, but because that is the restriction. So at the point of extrema also the phi will be satisfied, that means phi at xy has to be 0. So with this phi xy is equal to 0, if we differentiate here now with respect to x, so what we will get, del phi over del x, and then again there will be term dx over dx which will be 1, and then del phi over del y and dy over dx is equal to 0. So we have this another equation which is satisfied at the point of extrema. We have dy dx there, we have dy dx in this equation also, because at the end we do not want to see this dy over dx calculation. We have two functions, we have f xy and we have phi xy. So these partial derivatives of phi with respect to x or partial derivative of phi with respect to y, similarly the partial derivative of f with respect to x and partial derivative of f with respect to y, all these should come at the end in the picture of the calculation of those points of extrema. So, here we can eliminate this dy over dx from these two equations. How to eliminate? That this equation del phi over del x and del phi over del y over del x, we multiply by del f over del y divided by del phi over del y and add this first equation del f over del x and del f over del y into dy over dx. So, what will happen here? This phi y will get cancelled in the second term. With the minus sign we will get del f over del y dy over del dx, and here also we have del f over del y dy over dx. So, this term will get cancelled, and what we will get then? So, let us this ratio phi y over phi y we denote by lambda. So, then this equation here, what we get? We get del f over del x, and then there is a this term with lambda del phi over del x, because this gets cancelled with this. So, we have only these two terms. So, that is one equation. In terms of lambda, the lambda how it is related to phi y and f y, that is given here already, that lambda is equal to minus f y over phi y. We have just denoted for the sake of simplicity of our equations. So, this equation is simple now, del f over del x plus lambda del phi over del x, and all these equations, whether this one or this one, they all satisfy at the point of extrema. So, this is one equation we have which has to be satisfied at the point of extrema. We have this equation because that relation we have just set. So, the lambda must be related to this f and phi by this equation, that is our another equation, and naturally phi x y is equal to 0, that has to be satisfied at the point of extrema. So, here at the point of extrema these three equations must be satisfied. So, if we solve these three equations, what we will get? We will get those critical points where we will look for the extremum values. So, and how many unknowns we have? Of course, we will calculate x and y, and also this lambda is unknown because we have introduced this new symbol here lambda. So, lambda is also known. So, we have x, y and lambda. We have three equations, we have three unknowns, and we will see that we can get we can solve these equations and get these x, y and lambda. So, how to remember these three equations which need to be solved to get these candidates for extremums? This is the so called method of Lagrange multiplier. So, how do we remember these three equations? So, what are the working rules? The problem was we want to maximize, minimize this u is equal to f x y with the constraint phi x y is equal to 0. So, we define an auxiliary function. With the help of this auxiliary function, this will be easy to define all these three equations which we need. What is that auxiliary function? That is a function f x y and lambda. So, how do we define that? Just keep this function f x y which we want to minimize or maximize, plus lambda times the constraint, phi x y x comma y. Now, this function, this is a function of three variables, and we have only studied functions of two variables for maxima and minima, but at least those necessary conditions for extrema we have already studied, which can be extended for any number of variables. So, here we have three variables. So, these three partial order derivatives must be 0. So, if we get those conditions for extremum, those necessary conditions, then what we will get? What we will get, f x is equal to 0, the partial derivative of this f with respect to x. So, what we will get here? F x plus lambda and phi y. So, f x plus lambda phi x is equal to 0. So, that is the first equation we will get out of this auxiliary function which we want to now maximize or minimize, and then as a necessary condition, the first is that the partial derivative with respect to this first variable must be 0, and then we got this first equation which we have derived just before. Similarly, if we set f y is equal to 0, we will get f y plus lambda this phi y, this is equal to 0. That is the second equation we have there. The third will be f lambda is equal to 0, because the third variable is lambda. So, the partial derivative with respect to lambda must be 0, and here we got that this f x y plus this lambda phi x y, if we differentiate this with respect to lambda, then we will get just phi x y. So, here we will get phi x y is equal to 0. So, all the three equations which we have just derived here can be obtained by this auxiliary function by looking at the necessary conditions of this auxiliary function. And here we will not go for the sufficient conditions, that means we will not characterize the function for maxima and minima in this case, and we will restrict ourselves here up to these necessary conditions where we have to find the critical points of this auxiliary function, basically all the points which are the candidates for a maxima or minima. So, here there are a few remarks. So, using this method of Lagrange multiplier, we obtain stationary points, so the candidates for extrema, and we do not determine the nature of the stationary point. And in practice, we usually are interested in finding maxima minima or maximum minimum value of the function under given constraint. So, what will be done in this lecture, that we will not look for the nature of those stationary points which we will get using this Lagrange multiplier. We will just evaluate the function value at all these points and then see where the function attains its maximum. So, basically the global maximum and minimum. Usually there are few candidates, so the critical points. So, we can evaluate f at all of them and choose the largest and smallest values. Hence, no further test is required if we wish to find only absolute maximum or minimum. Let us go through the problems. So, here we have problem number 1, find the absolute maximum and absolute minimum of the function x cube plus 3 y square on the unit disk x square plus y square less than equal to 1. The same problem we have done in the previous lecture, where this was considered as the domain, the disk was the domain, and inside the domain we calculated the stationary point just by looking at the critical points of this function and checked with whether the critical points lie inside this domain. That was one part. On the other part, we have just looked at the boundaries. So, we have considered x square plus y square is equal to 1, that relation, and from here we had converted the problem into a problem of one variable. That means this y square was substituted here in terms of x square, and then the problem of one variable was optimized, one variable was solved using the techniques we know for functions of one variable. So, just to recall that what we have done, we have found the stationary point which was just 0 and comma 0 in that case, and this stationary point lies within the domain. So, this was considered as the candidate for checking the function value, and then along the boundary x square plus y square is equal to 1, we had converted the problem into a problem of single variable, and which was looked again for stationary point and then also the boundary points, and finally there were these 5 points. So, 0 0 was 1 point and there were 4 points here on the boundaries, and we calculated the function value at all these points and then realized that the maximum value is 3 and the minimum value is -1. The minimum is achieved at -1 comma 0 at this point, and the maximum was at x is equal to 0, y is equal to 1. So, at this point, also at this point, it was where the function achieved its maximum value. So, now the same problem we will look from the different aspect, as that we want to minimize or maximize this value, or we want to find minimum and maximum values of this function under the constraint. So, we will put that boundary x square plus y square is equal to 1 as constraint together with this function, and use the method of Lagrange multiplier and see what happens. So, we want to maximize, minimize this problem on the disk, this one. So, here we will consider this problem as that maximize, minimize this x cube plus 3y square subject to x square plus y square is equal to 1. The stationary point which we achieved before, that was the interior point, that will remain as it is. So, we have to compute the stationary point of this function and see whether any point lies within the domain. So, that part remains as it is, but for the second part, earlier we had converted the problem into a problem of one variable, but now we will use the method of Lagrange multiplier, and this x square plus y square is equal to 1, this constraint will be used as this boundary will be used as a constraint for the problem. So, now along this boundary x square plus y square, we want to basically have this problem now. So, at the interior point we have that stationary point, but along the boundary we want to solve this problem, maximize, minimize f x is equal to 0, f x is equal to x cube plus 3y square, and subject to this x square plus y square is equal to 1. So, the auxiliary function for the Lagrange multiplier we can formulate as x cube plus 3y square plus the lambda and the constraint, that is x square plus y square minus 1. So, this we will write x square plus y square minus 1 is equal to 0. So, that is the constraint x square plus y square minus 1, and we have here the function x cube plus 3y square. And now, we will find the critical points of this f x y lambda. That means, we need to solve f x is equal to 0, which will be from here we can get like 3x square, and here we will get 2x lambda is equal to 0. So, that will be the first equation. Here x we can take common. So, we will have 3x plus 2 lambda into this x is equal to 0. Similarly, this f y is equal to 0 we can get from here. So, f x y lambda is equal to 0, what we will get, it is 6y plus this 2y and lambda from here is equal to 0. So, again what we see that y if we take common and 2 is anyway not equal to 0. So, here we will get a 3 plus this, here we will get lambda. So, this is another equation what we have. And the third equation, by setting f lambda is equal to 0, is the constraint itself, because with respect to lambda when we differentiate we will get the second part, that is x square plus y square minus 1 is equal to 0. So, this is the constraint itself. So, these three equations need to be solved to get all possible these critical points for this second problem, where we have defined the auxiliary function. Okay, so we have these three equations which need to be solved now. So, from this equation, so sometimes the solving these equations could be tricky, because you have to find all those points which satisfy all the three equations. So, here from this y 3 plus lambda is equal to 0, because this is the simplest one among all. Here we realize that this derivative, I mean this equation will be satisfied when lambda is either lambda is minus 3 or y is 0. So, one of them or both of them has to be there, either lambda is equal to minus 3 or y is equal to 0. So, these are the two possibilities which can make this equation equal to 0. So, then let us take first y is equal to 0. So, from here we have fixed the y coordinate, y is equal to 0. Naturally, once we have y, we can get x from here. So, x will be plus minus 1. So, x is coming from this equation. Now, y is there, x is there. now we will get lambda so that this equation is satisfied. So, here the x is plus and minus 1. So, we have to use this x plus minus 1 here and get the possible values of lambda. So, when x is plus 1, we will get lambda minus 3 by 2, when x is minus 1, we will get lambda as plus 3 by 2. So, we have the points plus 1, then we have here 0 and then we have minus 3 by 2 for lambda. The second point we are getting minus 1, then 0 and here 3 by 2. So, these 2 points satisfy all the 3 equations. So, that is what we have searched now, but we have to further look at the other possibilities. For instance, here lambda can be minus 3, this equation will be 0. So, let us take that lambda is equal to minus 3. In the third equation we do not have lambda. So, we use lambda here in this equation and then get the corresponding x. So, if we use this lambda as minus 3, what we will get? We will get x is equal to 0, we will get x is equal to 2. So, if we use this x is equal to 0 here in the third equation, we can get y, that is plus minus 1, but this x is equal to 2 we will not get any y from this equation, because here x square plus y square should be 1. So, if y is 2 we cannot get any such x which can satisfy this equation. So, this x is equal to 2 is not possible as it cannot satisfy the second equation. So, we will ignore that. So, how so what we got here now? We got x 0, we got y 1 plus 1 and lambda minus 3. We also got 0 and then minus 1 and lambda minus 3. So, we got 2 more points here, and these are all possible points which can be which can solve these 3 equations simultaneously. So, these are the only these 3 points which we got as critical point of the given problem. So, the candidates for extrema, because we are not going for the sufficient conditions and all. So, this third, the lambda is not of our interest, because in the function only x and y will be there. So, we get only these 1 comma 0, minus 1 comma 0, 0 comma 1 and 0 minus 1, all these x y points. So, plus minus 1 0 and 0 plus minus 1, and these are exactly the same points which we got before in the earlier problem. And then for each of these points we will compute the function value and then find out where it is maximum or minimum. So, that problem is done in 2 different ways. One where we have converted the problem into a problem of single variable, and in the second one here we use this method of Lagrange multiplier. So, another problem here, we want to maximize, minimize this function x square minus y square minus 2x in this region x square plus y square less than or equal to 1. So, first we have to look for the local extrema in the interior x square plus y square less than 1 in this region, because there are the boundaries. Here one boundary which is x square plus y square is equal to 1, and we have this interior, the disk. So, what we have to look for? First we have to look for the critical points of this function and see whether it lies inside this domain. So, to get the critical point of this function, we will get this f x is equal to 0, which is just 2x and minus 2 from here, that means the x is equal to 1. So, that is x is equal to 1. The second, this f y is equal to 0 means 2 y is equal to 0, and from here we will get y is equal to 0. So, this is the only critical point which is 1 comma 0, that is the only critical point, but what we see that this point does not lie inside the domain, inside the disk. Indeed, this lies on the boundaries, but that boundary consideration we will see little later, and that will automatically be included there. So, basically in the interior part we do not have any critical point. So, we can ignore in fact this point also, because that will be a point on the boundary. So, this point lies on the boundary. So, no critical point lies in the interior. This is what we have observed in this case. Remember, in the earlier problem there was only one critical point, that was 0, 0, which was inside the domain, and we had considered for the extremum values. Now, the local extrema on the boundary, that is x square plus y square is equal to 1, and here we maximize or minimize this x square minus y square minus 2x subject to this x square plus y square is equal to 1, subject to this boundary, subject to this constraint. So, the auxiliary function for the Lagrange multiplier, what we have, x square minus y square minus 2x plus this lambda, and then we have x square plus y square minus 1, this constraint, and then we will find the critical points. So, f x is equal to 0, if we set, we will get here 2x, we will get minus 2, and then from here also we will get 2x lambda. So, that will be the one equation which we have, just if we take common from here x, then we will get 1 plus lambda and is equal to 1. So, that is the equation number 1. F y equal to 0, then minus 2 y, and then here 2 y lambda, here we will get one more equation, and f lambda is equal to 0, the third equation will be just the constraint, the given constraint, x square plus y square is equal to 1. So, we have all these three equations, and now we will solve for x, y and lambda. So, again these three equations are written here, y lambda minus 1 and x square plus y square is equal to 1. So, again it looks like it is easy now first to start with this equation y lambda minus 1 is equal to 0, because the solution is readily available, that this will be 0 for y is equal to 0 and lambda is equal to 1. So, these are the two possible solutions for this, y is equal to 0 and lambda is equal to 1. Let us take 1. So, y is equal to 0, from here we can get then x as plus minus 1. So, x is there, y is there, and from the third equation we will fix our lambda. So, x is plus 1, then lambda will be 1 plus lambda is equal to 1, then we have lambda 0, and when x is minus 1 we will get lambda as minus 2. So, the first set of equations we got from here, it is like 1 plus 1, then y 0, and then we have lambda 0, another one we have minus 1, 0 and minus 2. So, these are the 2 points we got already. Now, this lambda is equal to 1 we will fix for the second equation, and the lambda is here now in the first equation, which is fixed now, lambda is equal to 1, but we can get now the x is half, and when we fix this x is equal to half here in this third equation, we will get, because x is half means we have 1 by 4 plus y square is equal to 1. So, y square is 3 by 4, and then y will be plus minus square root 3 by 2. So, that is y. So, here we got another 2 points with x half, y square root 3 by 2 and lambda 1. Then we have half, y is minus square root 3 by 2, and then this lambda is half. So, these 4 points we got as critical point of this new problem. And now, since we are not looking for the sufficient conditions, so the third point is not of interest, we will just collect the x and y coordinates. So, what we have, the candidates for extrema, plus minus 1 0, we have half and plus minus square root 3 by 2. So, these 4 points. So, as you can see, this the point which we got earlier on the boundary, it is already there, plus 1 0. So, here now we will get the function values at these points. So, 1 comma 0, minus 1 comma 0, and then here half and plus minus square root 3 by 2. Why we have taken together plus minus? Because y square is there, the value will be same at all at both the points. So, at 1 comma 0, the value will be 1 minus 2. So, that is minus 1. Here on minus 1, the value will be 3, and then here minus 3 by 2. So, what we realize that the maximum value of the function is 3 here at this point minus 1 0, and the minimum value of the function is minus 3 by 2 at the point half plus minus square root 3 by 2. So, in this way we can maximize minimize the problem using this Lagrange multiplier by finding out all possible critical points or the candidates for the maximum and minimum values. This is the last problem. So, here we want to maximize or minimize this function x square plus y square subject to this restriction that x minus 2 whole square plus y minus 1 whole square is less than 20. So, this is also a similar problem which we have just handled before. First, we have to look for the local extrema in the interior of this domain. That means setting the f x is equal to 0, the f x was x square plus y square. So, you will get x 0, y 0. So, that is the critical point x is equal to 0, y is equal to 0, which is there in the domain. So, we will consider this one. Now, at the boundary, so we have this is the boundary. So, we will maximize minimize this x square plus y square subject to this restriction on x and y. That means, using this Lagrange auxiliary function, we can get all the critical points. So, this is the Lagrange using Lagrange multiplier, that is our auxiliary function, and now we can get from this auxiliary function all critical points by setting f x is equal to 0, which is just from here we can get like 2x plus here 2x minus 2 lambda. So, that will be the simplified equation there. F y is equal to 0, we will get this equation, and f lambda equal to 0, that is the third equation, which is the given constraint. So, from the first equation we can get this x minus 2 in terms of lambda. So, we have to just simplify this one. So, it is like x if I take common. So, we have 1 plus lambda and the right hand side will be 2 lambda. So, here the x will be 2 lambda over 1 plus lambda, and the x minus 2 we want to compute, then 2 lambda over 1 plus lambda and minus 2. So, this if we simplify we will get this minus 2 over 1 plus lambda. Similarly, from here also x minus y we can get, and now if we put this x minus 2 and x minus y in this equation, what we will get? We will get the possible values of lambda from this equation plus minus half. That means, lambda will be minus half or minus 3 by 2, these two possible values. Accordingly, we will get y minus 1 or 3, x we will get minus 2 and 6. So, these are the possible solutions for these three equations. That means, we have the point minus 2 and minus 1, we have the point 6 3, and there was a point in the interior 0 comma 0. So, we have to compute the function value at all these 3 points. Here the function value is 0, at this it is 5, and here is 45, and now we see that the minimum value is 0, which is attained at the origin, which was natural. Looking at the function also one could have realized at the very beginning, but the maximum value which lies at 6 comma 3 is on the boundary here, and the value is 45. Well, so just to conclude, we have gone through this method of Lagrange multiplier, which is used for solving such problems. U is equal to f x y, which we want to maximize minimize under certain restrictions on x y, some constraints. And the process is to define the auxiliary function, where we just take this f x y plus lambda phi x y and look for the necessary conditions of extrema for this big F, and then by setting this f x is equal to 0, we get one equation, f y is equal to 0, we get another equation, f z is equal to 0, we get the third equation. By solving these three equations, we get all the points there, and then at all those points the function value can be computed. So, here we have the references which are used for preparing this lecture, and with this I thank you for your attention.